Hello, I am Maram Khatib, a postdoc at the Robotics Lab of Sapienza University of Rome. It's my pleasure today to introduce our work about a human-robot contactless collaboration with mixed reality interface. This work is done with my colleagues Khaled Al-Khudair and Alessandro Di Luca. The capability of handling tasks that involves interaction between humans and robots is one of the enabling technologies of Industry 4.0. In today's industry, the quality assurance phase is controlled manually by the operator, and robot does not aware about human action. Alternatively, it is significant to upgrade this process to be autonomous by exchange beneficial information between the robot and the operator. The goal of our research work is to define a framework of achieving a number of collaborative tasks that require coordinated robot-human motion, by integrating a suite of sensors in order to monitor the workspace, safely control the robot so as to avoid accidental collisions, and to provide the user with the awareness of ongoing interaction tasks. The proposed multi-sensor control scheme for safe human-robot contactless collaboration consists of three main systems. First, the task management system to be defined a suitable end effector Cartesian task according to the online operator input, current operator's pose. Next, the collision avoidance system to avoid any robot collision with the human operator body and with all nearby obstacles. Priority control to execute optimally the desired tasks in the presence of hard bounds on robot actuation. This involves exploiting the available kinematic redundancy of the robot as well. Several sensors are involved in the task management system. Oculus Virtual Reality System is used to track the human pose localization. Using the Rift controller, the operator can select the desired task from the mixed reality interface presented in the human-mounted device. A stereo camera is mounted to the Oculus Rift to render the surrounding workspace of the operator, enabling the mixed reality experience. We define several collaboration modes for our application. Each mode consists of positional task and relaxed pointing task. In the follow and circle modes, the tip of the robot should follow a desired positional task attached to the moving Oculus Rift position, PS. In stop mode, the robot should regulate to the last computed desired point and remains at rest. In the all previous modes, the robot should also point approximately toward the human head, and in fact should only belong to the surface of the pointing cone. The cone is again determined from the estimated head pose. The user can determine online the desired angle, alpha D. During the human-robot coordinated motion, some limits may be violated when the operator moves outside of the robot workspace, where the desired positional and/or pointing task cannot be fully filled according to the current operator pose. For this situation, we propose a special treatment for the desired task to avoid any operational task singularity. We define a Cartesian boundary around the robot by a virtual sphere. If the human head goes beyond the bounding sphere, the desired task position will be accordingly reallocated at the intersection point between the human line of sight and the sphere. If the operator is looking outside of the robot workspace, the desired task will not be updated and the motion control is resumed with the last estimated pose. To guarantee human safety and robot integrity, a single depth sensor is used together with the depth space approach to evaluate the distances between a number of control points along the robot arm and any obstacle in the workspace. According to these distances, the repulsive vector associated to the end effector control point is determined and directly modifies the end effector original desired positional task. While the repulsive vectors associated to control points along the robot body are treated as Cartesian constraints with artificial forces that are translated into hard joint constraints. For robot control, we apply the simplest version of the saturation in the null space algorithm at the acceleration level. Considering the joint limits, which already embed collision avoidance for the robot body, and exploiting robot redundancy to realize the other desired tasks as much as possible, according to the following priority: collision avoidance, end effector positional task, and end effector pointing task. In the experimental setup, we have considered a KUKA LWR4 manipulator. The proposed control system is implemented using C++ through the ROS2 middleware. The robot is commanded using a control cycle of 5 milliseconds. During the experiment, the operator head position is always out of the predefined sphere of task limits. The corresponding projection is used to define the reference value for the coordination task. The difference between the actual end effector position and the desired one is due instead to obstacle avoidance. The large initial values of tracking error are due to the relatively fast motion of the human operator. These errors can be reduced by increasing the motion control gains. However, a trade-off between low Cartesian errors and high end effector velocity should be taken into account. The successive increase in the position error are due instead to obstacle avoidance, as indicated by the 3 peaks in the end effector reaction magnitude. The velocity limits scaling factor are reduced according to the robot body control points that are more influenced by the presence of obstacles. For example, at this period, an obstacle is getting closer to the first and second joints, resulting in a modification of the actual joint limits, and thus in a robot reconfiguration in its joint space. However, using the SNS algorithm, the robot is able to exploit the available redundancy to follow accurately the desired end effector position while avoiding the obstacle. As a conclusion, our proposed framework is compatible with the robot safety standard and technical specification, where, following the Mod 1 SMS, the robot immediately stops when the collision cannot be avoided. Also, the end effector desired velocity and distance d can be determined according to the recommended protective distance of Mod 3 SSM. For the full details, please refer to our published article. Please share with us any comments or questions using this email. Thank you.